or only mass action law we have seen?
Yes, sir, mass action law completed. So one example that energy of photon of a sodium that completed.
Okay, 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 fine. Okay, now let us start with electrical conductivity of semiconductors. Is the screen visible, Evan?
Sir, visible, sir.
Visible. Okay, now first of all, draw this diagram fast.
Sir, sir, drawn, sir.
Drawn. Now I have seen this diagram. This is a piece of a cylindrical conductor, okay? Or we can imagine it is a large piece of wire. Okay. Now, had it been a wire, the conduction will be very easy. Okay, just free electrons they will transfer. Now here we have to see the same about semiconductor. So here we have taken a cylindrical semiconductor of length L and area of cross section capital A. Okay. Now when we apply a potential difference V across the ends, then what will happen? Then because of the battery, an electric potential difference will be formed across the two ends of semiconductor, right?
Yes, sir.
Right? So because of that electric field, what will happen? Positive charges will move away and negative charges will move towards the positive charge. Okay. So positive charges will move along the electric field and negative charges or electrons will move away from the negative charge, or that is they will move towards the positive charge. Okay. Now what will be the total current flowing here? Total current flowing, we know that it will be whole current plus electron current. Okay. Sum of both the currents will be here, right? Yes, got it.
Sir, got it, sir.
Therefore, if Ne is the number of conduction band electrons, means this much electrons are in conduction band, and Ve is the drift velocity. Ve is the drift velocity. Then what will be the current? Current will be NeaVd. Okay, this we have seen in current electricity, right? NeaVd is the value of current, where Vd is the drift velocity, right?
Yes, sir.
So this is what? This is value of current. This is drift velocity. Vd is the drift velocity, E is the charge of an electron, A is the area of cross section, and Ne is the number of free electrons. Okay. Similarly, whole current will be what? NeaVd. Now here, instead of Vd, we will use drift velocity of holes, that is Vh. Getting it? So NeaVh. So from here, we will get total current, that is NeaVe plus NHEAVH. Here Ne and NH are number of holes and number of electrons respectively. Okay.
Yes, sir. So got it. Done, sir.
Got it?
Yes, I got it, sir.
Take it now. Now this is the current. We know that if rho is the resistivity, then what is resistance? Rho L by A is the resistance. Okay, and we also know that V equals to IR. So here apply Ohm's law, V equals to IR, and instead of R, write rho L upon A. Okay, instead of current, write down the above derived value. Okay, now area of cross section will be cancelled out. Rho LE into NEE plus NHVH. This is what we are getting as potential difference. Nothing we did, we just substituted the formula of resistance rho L by A and the formula of Ohm's law, V equals to IR.
Sir, done, sir.
Done? Now again, we know that electric field is what? Potential gradient. Means when we differentiate the potential with respect to x, we will get electric field. That is V upon L. Okay, so take L on the opposite side, V upon L. Take this L on opposite side. This is L. Take this L here. We will get electric field. Okay, electric field equals to rho into E NEVE plus NSVH. Okay. Now again we can do a thing. Take rho on that side and take electric field on this side. Electric field will come in division. Now see this VE upon E, potential upon electric field. Here also potential upon electric field. So what we are getting? Potential upon electric field, we actually define it as mobility. Mobility. Okay. Potential or sorry, drift velocity divided by electric field, not potential. This is drift velocity divided by potential will give us what? Mobility. Take it down to this point.
Sir, done, sir.
Then
Sir, done, sir.
Then now here we are defining a new thing which is called mobility. Mobility is nothing but the ability of electron to move inside a semiconductor. When we are applying electric field, the drift velocity is acquired by electrons or holes. Okay, and it starts moving. So we are here calculating that with this much electric field, how much velocity is getting generated. This we are calling as mobility. Mobility is drift divided by electric field. So velocity per unit distance of electric field. So this is called mobility. It is denoted as mu. So when we use mobility, it will become 1 upon rho equals E into N E mu T plus N H mu H. Whereas mu E and mu H are mobility. And we know that 1 upon rho was the resistivity. Inverse of rho is conductivity. Got it?
So got it, so done. Sir, done, sir.
Done?
Yes, sir, done, sir.
Now, see this question.
Yes, yes, sir. So 3 into 10 power minus 6 we can.
Fine. How? This is simple. Okay, we just want to calculate the conductance. Okay, conductance means simply sigma we need to calculate. Okay, and everything is given to us. Just put them in the form. Answer. Now next is PN junction. What is a PN junction? Yes. A PN junction is nothing but a very basic building block of semiconductors. All the semiconductors, whatever we see today, are just PN junctions. Nothing. How a PN junction is formed? A P-type semiconductor and N-type semiconductor, they are just joined together. Just joined together. Okay. What is a P-type semiconductor? Now let us recall. Yes, Iman. Am I audible?
You are audible, sir. Yes, sir. You are audible, sir. Yes, sir.
Okay, okay. So what we do? Just a minute. Yes, now. So in PN junction, what is happening? A P-type and N-type semiconductors are being fused together. Now, what is a P-type semiconductor here? P-type semiconductor is one in which positive charge carriers are the majority charge carriers. Positive means holes. So holes are majority in which type of semiconductor? Which is doped with a trivalent impurity. Getting it? Which is doped with a trivalent impurity in that one place is remaining that will act as hole. Okay? It is not negatively charged or positively charged. It just have a place for hole, a place or hole, empty place is there in which an electron can be fitted. Getting it?
So getting sense.
So this is the thing. PN junction is made up of two semiconductors, different type of semiconductors fused together. And with the help of this PN junction, we have formed all of this electron. Now there are special techniques with which this semiconductor can be made. First one is alloy method. Okay. In alloy method, a small piece of group 3 impurity like indium is placed over N silicon or N germanium and melted. So what will happen? It will make a PN junction. Getting it? Generally use indium, and this forms an indium button which acts as a PN junction.
Sorry, sir. For copied, sir.
Done?
Done, sir.
Now next is diffusion method. In this diffusion method, what we do, we just take a plate of N-type semiconductor. N-type semiconductor is generally germanium or silicon. Okay, and it is heated amid in the vapors of impurity, generally aluminum. So that aluminum will be deposited over the surface of this N-type germanium or silicon. This diffused surface now will act as a PN junction. Okay.
Sir, done, sir.
Done. Now next is epinectin junction or vapor deposited junction. In this, what happens? P-type wafer is kept in an atmosphere of silane. Silane is actually a silicon compound at high temperature. it dissociates into silicon, means it is a compound, and silane having silicon. But when it is heated, the silicon starts getting deposited. So a p-type silicon wafer is put in this region, having these vapors, phosphorus vapors, as well as this silane compound. At high temperature, this silicon will be deposited over this p-type silicon wafer. This is p-type, and the layer deposited will be of n-type. So what do we get? We get a p-n junction now. Okay. So this is how a p-n junction is formed.
So done, sir.
Done? Now, as soon as silicon wafer is kept in the above three methods, it may form a p-n junction, and immediately a p-n junction is formed, some process will start happening. See, we know that p-type semiconductor has more number of holes as majority charge carriers, and n-type semiconductors have electrons as majority charge carriers. Now remember one thing, they have just majority charge carriers. It does not mean that they are positively charged or negatively charged. Getting it? Hello? Yeah, am I audible?
Sir, you are audible, sir.
Now, see, when they are joined now, so at one side holes are more in number, and at another side electrons are more in number. So what will happen? The electrons will start diffusing. Electrons will start diffusing from n-type to p-type. Okay. Why this will happen? This will happen because they are more in number. So diffusion you might have studied. Yes, am I audible?
Sir, you are audible, sir. You're done, sir.
That. Okay. So now due to this concentration difference, electron from n side and holes from p side diffuse it to the opposite side. This motion of charges will give us a diffusion current. See, what is current? Current is motion of the charges, is it not? And when the charges are moving, they will constitute electric current. Okay. So an electric current will be formed. An electric current will be formed, right?
Yes, sir.
Take it down.
Taken down, sir. So done, sir. Taken down, sir.
Done. Now, a layer is formed in between these two types of semiconductors, N-type and P-type. This region on either side of the junction is called depletion region. Why? See, when holes are moving towards N side, their space is empty now. On P side, getting it? Their space is empty now. It means what? The charge carrier which was present earlier is now absent. So, in absence of charge carrier, no current will be there. This is called depletion region. Why it is called depletion region? Because the charges are not present in it now. Okay, charge carriers are not present in it. Okay.
Yes, sir. Okay, sir.
Got it?
I got it, sir. Yes.
Now this depletion layer is very, very, very thin. It is of the order of 10 to the power minus 6 meters, micrometers, okay? And as the temperature increases, this depletion layer will also increase. Take these points down.
Sir, done, sir. You're done, sir.
Now, next, now what we do? Because of this movement of charge, a current is formed that is called diffusion current that we have seen. Now the loss of electrons from N region and gain of electrons by P region. In P region there was holes. So electrons got inside those holes and recombined them, filled those holes. So N region is losing electrons, P region is gaining electrons. Okay. Because of this, a potential difference will be created between the two regions. Okay. And since this potential will do what? This potential will stop the further movement of electrons from N to P. Getting it? So that's why this is called barrier potential. Why it is called a barrier potential? Because of this. Because of the movement of charges, what will happen? An electric field will be produced, and that electric field will now oppose the further movement of electrons. This is called barrier potential. Okay. For germanium, this barrier potential is 0.3 volt. and for silicon it is 0.7. Draw this diagram and take this point down.
Sir, done, sir.
Done? Now, now here I just told you that an electric field will be produced. This electric field, due to this potential barrier, is nearly 10 to the power 5 volts per meter. And as this current continues to flow, this electric field will go on increasing and increasing till the point both are balanced. Means electric field is stopping all of the charges from moving. Okay. At a point, a situation occurs due to this increased electric field in which electron on p side of the junction moves to n side of the junction, and a hole on n side of the junction moves to p side. This motion of charge carriers due to the electric field is called drift. Thus, a drift current which is opposite in direction to the diffusion current, it starts. Why it is starting? Again, because after some time, electric field will become much more powerful. It will start carrying holes back to their original place and electrons back to their original place. So this is called a drift current. So generally in equilibrium, this drift current is equal to diffusion current. Both are equal and opposite. Take it down.
Sir, done, sir.
Then so we have two things. Diffusion current from P to N side and drift current from N side to P side. Right? And if there is no biasing means we are not doing anything, we are not applying any battery. Because of battery, bias occurs. So when battery is not there, then diffusion current is equal to the drift current. Okay. Now, what is this biasing? What did I say just about this biasing? Biasing means a fixed DC voltage or a current is applied to a terminal of an electric component, such as a diode, transistor, etc. This is called biasing. Okay. So this type of biasing or potential difference I am not applying.
Sir, done, sir.
Now next is semiconductor diode. See, this is from now I hope till this point you understood how these PN junctions are working. Okay, what is happening in PN junction? First of all, we came across semiconductors like germanium and silicon. Next, we just doped them with impurities, pentavalent or trivalent. Okay, so that we formed the N-type semiconductor or P-type semiconductor. These were extrinsic semiconductors. Okay. Now these N-type semiconductor or P-type semiconductors, we just joined them together and we got a PN junction. We got PN junction. Now what is happening in this PN junction? We saw the theory. Now let us move towards application. That is semiconductor diode. This diode is the easiest one. This is the basic building block of all of the electronics, whatever you are going to study in future. So a semiconductor diode is nothing but a PN junction. A PN junction with metallic contacts provided at the end for application. Okay, for application of any external voltage. So this is a two-terminal device. So what is happening here? In between two metallic contacts, a P-type semiconductor is there and an N-type semiconductor is there. So in between them, naturally a depletion layer will exist. Okay. So this device we call it a diode, semiconductor diode. Draw this diagram, take it down.
Sir, done, sir.
Done? Just a minute. Now, this semiconductor diode is also depicted as this, the general uh, sign for diode for drawing in the circuits. Okay. Take it down.
So done, sir.
Done. Start. Now PN junction under forward bias. PN junction under forward bias. The bias we have studied now. Forward bias means when we connect positive side of the battery to the P type and negative side to the N type, then it is called a forward bias. Okay. Draw the diagram.
So done, sir.
Done. Now, see, when a positive terminal is of a battery is connected to a P side and negative terminal is connected to N side of a PN junction, then it is said to be forward biased. Okay, then it is forward bias. Now, in forward bias, what is happening? Holes are repelled from the positive terminal. See, because positive terminal is now more positive, so holes will be repelled. Or because positive and positive will repel each other. So holes are repelled from the positive terminal and compelled to move towards the junction. And the electrons are repelled in the negative terminal and they will move towards the junction. This will reduce the depletion layer. Means depletion layer will get thinner. Okay. And what will happen? The potential barrier will be reduced because the depletion layer is thinner now. Take down these 3 points first.
So done, sir.
Done. Now what will happen? The charge carriers on both the sides will start diffusing towards the opposite side, and this give rise to net current, which is called forward current. Means when we join a battery, we will get a forward current. Okay, and this forward current is nothing but sum of hole current and electron current. These were what? These were diffusion currents. Hole diffusion current and electron diffusion current. Take it down to this point.
So done, sir.
Done.
So done, sir.
Okay. Fine. Next is PN junction in reverse bias. In reverse bias, what is happening? We are connecting the battery in reverse order of the previous case. Positive terminal of the battery is connected with N side and negative terminal is connected with P side. Okay. This is called reverse bias. Now, what happens when the diode is reverse biased? We shall study it in our next class tomorrow. Okay.
Yes, sir. Okay, sir.
Got till this point? See, this chapter is mostly theoretical, so please do revise whatever we are listening here in the class. Please do read it. Okay, and this chapter will be just firm in your mind when you just read it again and again. Okay.
Yes, sir. Okay, sir.
Fine. Okay then. That's all for today.
Yes, sir. Thank you, sir.